In this video, we will have a look at deep neural networks and methods that can deal with overfitting. Deep learning refers to neural networks with several hidden layers that are used in, for example, deep neural networks, recurrent neural networks, and convolutional neural networks. An artificial neural network generally consists of input nodes, a hidden layer, and output nodes. When the network consists of more than one hidden layer, it can be referred to as a deep neural network. In this case, the network consists of two hidden layers. By adding more hidden layers, we will get a deeper network. A deeper network can learn more complicated patterns. In this video, I will try to explain why that is the case and how that is related to overfitting. Suppose that we have the following dataset, where these 6 individuals are known to be infected with some pathogen, whereas these 5 individuals are known to be healthy. One has measured the body temperature in Celsius of these 11 individuals. Fever is usually defined as a body temperature above 38 degrees Celsius. The data can be plotted like this, where the infected individuals are coded as 1s and the healthy individuals as 0s. We will now use the simplest possible neural network with just one input node and 2 output nodes. Note that this network does not include any hidden layer. To train a neural network, one usually first normalizes the data, by for example using the mean-max normalization. This is the normalized data that will be used as input values in the input node. For example, this normalized value has been computed based on the original value, the minimum value, and the maximum value in a dataset. Training a neural network means that it finds the optimal values of its weights that are multiplied with the input nodes. The network also finds the optimal value for the so-called bias weight. Since we only have one input node in this example, we can remove this summation notation and write the equation like this. A network is also based on some sort of activation function. In this case, we use the sigmoid activation function that looks like this. If we train this network, we might obtain the following weights. If we like to predict the probability that a person is infected, we plug in the weights in this function. Suppose that we like to compute the probability that a person with a body temperature of 37 is infected. We therefore first normalize this value and plug in this value in the input node, which means that the value is then used in this equation. If we do the math and plug in the value of Z in the activation function, we will get the value of about 0.38. This means that the probability that a person with a body temperature of 37 is infected is about 38%. The probability that the person is healthy is simply 1 minus 0.38. If we compute the same thing for a range of different values between 0 and 1, and convert these normalized values between 0 and 1 back to their original scale, we will be able to draw the following curve that shows the probability that a person is infected given a certain body temperature. Let's plug in this expression here, so that we have the function of the curve. This mathematical function is actually the one that is used by the network when the value of this output node is calculated, which is the predicted probability of being infected. Note that this simple network is basically the same as logistic regression. To predict if a person with, for example, a body temperature of 38 is infected, we can draw a vertical line from 38, and then a horizontal line from the curve to the y-axis. We see that the corresponding value of the y-axis is about 1. We will get a more accurate value if we plug in the normalized value here and do the math. A common threshold to make a categorical prediction based on a probability is 0.5. Since this probability is greater than 0.5, we predict that a person with a body temperature of 38 is infected. By changing the bias weight, we can move the curve to the left or right. By instead changing the value of the weight that is multiplied by the value in the input node, we can change the slope of the curve. If we increase the value of this weight, the curve becomes steeper, and if we reduce this value, the curve is less steep. If the value is negative, the curve may result in a negative slope. A curve that makes the best prediction and fits best to the data is clearly a curve with the following values of the weights. Now, suppose that we instead have the following data, where two infected individuals now have a very low body temperature. If we use this simple neural network, it will fail to discriminate healthy from infected individuals because it can only generate this S-shaped curve. What we want is a curve that looks like this. If we add a hidden layer with two hidden nodes and train the network based on this data, we might obtain the following weights. The network now uses this complicated equation to compute the predicted probability of being infected, where this value is the bias weight for this output node, and this is the weight which is multiplied by the value inside this hidden node. The value inside this hidden node is determined by this bias weight, and the weight which is multiplied by the normalized body temperature in the input node. If we change the value of x norm between 0 and 1, we can generate the following curve that fits the data. We have therefore created a model that correctly predicts the individuals as being healthy if they have the body temperature between 36 and 37, and correctly predicts people that are outside this range as being infected. Now, suppose that we would move this data point to the right, like this. If we train this network on the new data, we see that it correctly predicts all infected individuals as being infected, and almost all healthy individuals as being healthy. This healthy individual will be incorrectly predicted as infected. However, this data point seems to be due to measurement error, because no healthy person should have a body temperature of 38.4. The network therefore makes a great job of ignoring this data point and predicting it as being infected. But what would happen if we instead use a deep neural network with two hidden layers? Well, such a deep network may actually generate the following strange curve, where this healthy individual is now correctly predicted as being healthy. This is the cool thing with deep neural networks, because they can learn almost any pattern in the data. However, is this network really useful? Suppose that we would use the following network to predict if someone is infected or not. It makes sense that people with a body temperature between 36 and 37 are predicted to be healthy. But it makes no sense that a person with a body temperature of exactly 38.4 is predicted to be healthy. By using a too deep network with many hidden nodes usually results in what we call overfitting, which occurs when the network fits well with the training data, but does not fit well to a new dataset. The reason why this network does not fit well with a new dataset is because this person who is infected is now incorrectly predicted as being healthy because his body temperature is 38.4. A network with just one hidden layer will do a better job of predicting the new data, because such a network will predict that people with a body temperature between 36 and 37.2 are healthy, whereas people outside this range are predicted as being infected. So for this data, it would make sense to use a simpler network, or to use a deep neural network where we use a method to prevent overfitting. We will discuss two such methods in a few minutes. But let's first take another example where we like to train a network based on some car sales data, so that we can use the network to predict an appropriate price of a used car based on its age. The input for our network will be the normalized ages of the cars, whereas the target values will be the normalized prices. We will first start to use the following network without any hidden layer, with just one input node that takes the normalized ages of the cars, and one output node that generates the predicted normalized price. We will here use the linear activation function for the output node, which means that the output node is simply equal to Z. Since we only have one input node in this example, we can remove this summation notation and write Z like this. Let's substitute Z with the terms on the right hand side, so that we get the following function that the network uses to compute the predicted normalized price based on the normalized age. If you train this simple network on the normalized data, we see that the bias weight is equal to about 0.83, and that the weight associated with the input node is about negative 0.88. These are the exact same estimated parameters we will get if we would use linear regression on the normalized data. By changing the value of the input node between 0 and 1, we can compute the predicted normalized price. If we then convert the normalized age and price back to the original scales, we will be able to add the following line, which shows the predicted car prices by the network. This is the exact same line as we would get if we would add a regression line to the data. For example, the network predicts that a car that is 4 years old will have a price of about 18,000 euros. Although a straight line fits quite well with the data, it does not account for the fact that the price declines faster for newer cars compared to older cars. If we instead use a network with one hidden layer that uses the sigmoid activation function to compute the values in the hidden nodes, the curve now fits better to the data. We see that the data points are now much closer to the curve compared to if we use a network without any hidden layer, which can only generate a straight line. The network now predicts a faster drop in the price for newer cars and a slower price fall for older cars. However, it is a bit strange that the price declines slower here compared to here. A curve like this seems more reasonable. We'll come back to this kind of curve later on when we apply the method of early stopping. Anyway, to measure how well the network fits the training data, we can, for example, calculate the sum of the squared errors. An error is the difference between the observed price and the predicted price by the network. If we would sum all the squared errors, then we would get a value of about 7.7. The smaller this value is, the better the model fits the data. However, if we instead use a deep neural network with 2 hidden layers, the curve now goes through every data point, which will result in an error that is almost 0. Although this model fits the data perfectly, it does not make sense. Because, for example, this peak suggests that the price suddenly increases after 9 years, which happens also around 4 years. Suppose that we would remove the training data and collect a new dataset that the network has not been trained on. Then we see that the network predicts the new data quite badly. Because, for example, the curve is quite far away from this data point. This is what we call overfitting, which means that the model fits very good to the training data, but does not fit well to the dataset that the network has not been trained on. The sum of the squared errors is therefore very small when we compute it based on the training data, but much larger when we compute it based on the new data. So, how do we prevent a deep neural network from overfitting? Well, there are several ways that we can do this, but I will here explain 2 common methods, early stopping and dropout. I will now show the method of early stopping, which requires that we have access to training data which the network will train on, and to some validation data that is not used during the training. The validation data is instead plugged into the network after it has been trained to see how well it can predict new data. A neural network is usually initialized with random values of the weights, which means that before the training starts, we usually get a bad fit to both the training data and the validation data because the data points are far away from the curve. Initially, the sum of the squared errors, SSE, will therefore be very large for both the training data and the validation data. Training a network means, in this case, that its weights will be updated to reduce the error. This is done with an iterative procedure. Once all data points have been used during the iterations, that is called one epoch. Watch the video about stochastic gradient descent to understand the difference between one iteration and one epoch. After a few epochs, where the weights have been updated, the curve starts to fit better, and the SSE value is therefore reduced. After more training, the curve starts to fit better and better and better. After about 100 epochs, the network starts to fit quite well with both the training data and the validation data. However, if you continue to train, the model starts to overfit because the SSE value starts to go up for the validation data, and the curve starts to look a bit strange. If you continue to train even more, we start to get a bad fit to the validation data, but almost a perfect fit to the training data because the training error is almost zero. Although the network fits perfectly with the training data, it fails to generalize well on unseen data. This explains the concept of overfitting. Early stopping means that we stop training the network when the error of the validation data starts to go up. In this example, we would run only 100 epochs because that amount of training results in the lowest validation error. The shape of the curve resembles quite well how we would expect the price should decline for older cars. By using early stopping, we have therefore obtained a network that can generalize well on unseen data. Another method to prevent overfitting is to use the dropout method. I will use the previous example to explain how the method of dropout works. During training, the dropout method randomly deactivates a fraction of nodes, usually the nodes in hidden layers, during each training iteration. The probability of a node being deactivated is determined by the dropout rate. Usually one uses a dropout rate of 0.5, which means that in every iteration during the training, a hidden node is deactivated by a probability of 50%. Suppose that we would train this network where we here use the body temperature of this patient to compute the probability that this person is infected. We normalize 36.1 and plug in the normalized value in the equation and do the math. Since this value is close to 0, the network correctly predicts that the person is healthy, which means that the network barely needs to change the values of the weights because the predicted value is close to 0. But what would happen if the dropout process deactivates, for example, this hidden node? Well, that would mean that this part of the equation would be set to 0, and that the predicted value is now 0.996, which is a bad prediction because the healthy person is now predicted as being infected. This means that the network will start to change the weights towards a worse fit to the data because it tries to correct the error. After the network has updated its weights, it takes the next input value. Now, suppose that this node would be deactivated, which means that this part of the equation is set to 0. However, deactivating this node does not affect the predicted value that much. Although we have deactivated one node, the network still correctly predicts this observation. By using the dropout method, we disrupt the training process, which prevents the network from learning too well. By using dropout, we We can therefore reduce the risk of overfitting. This was the end of this basic video about deep neural networks and how to deal with overfitting. Thanks for watching.